Hey, and thanks for watching the Multiplying Polynomials Lesson 3-2 video. By a suggestion from one of your peers, I'm going to split the lesson into two parts because it's so long. You may remember that the original lesson 3-1 was actually 24 minutes long. You guys saw 21 minutes of it, and it was only 3 pages. Well, lesson 3-2 is 7 pages long. So I'm going to split it into 2 parts, and I've pared down some of the material for you. I've gone ahead and added some of the notes on the note sheet, so you can go ahead and pause the video and add those when you need them to. Also, if you don't already have a highlighter handy, then please go ahead and get one. Of course, if you're watching this for the first time, you should just watch and listen anyway, and wait until the second time watching it to take notes. But in any event, make sure that you have your note sheet, a highlighter, and a pen ready. Okay, so this is lesson 3-2, multiplying polynomials, part 1. We're going to go through examples 1, 2, and 3. I have highlighted a reminder of the product of powers property, where if you are multiplying the same base and different exponents, you simply add the exponents. We're going to be using this when we're talking about distributing and multiplying the polynomials. So, example 1. We're working through the distributive property here, starting with just distributing a monomial through a polynomial. Each piece is multiplied by the monomial on the outside, and then we are simplifying. So 4x squared times 2x cubed, they've simplified to 8x to the 5th, and 4x squared times negative x squared is negative 4x to the 4th, and 4x squared times 5 is 20x squared. This looks really blurry to me. I'm assuming it does to you guys, so I'm going to try to zoom this in a little bit and crisp it up. Oh, that's much better. And I can get it to line back up again. Great. Or for the most part. So for part A of example 1, you should have 8x to the 5th minus 4x to the 4th plus 20x squared. And again, if I'm going too fast, feel free to pause it. Feel free to rewind it. Do whatever you need to do. I am trying to make these videos a little bit shorter, so I'm just going to keep moving, and you can just pause it if you need to. So, example B. They're showing us 2 methods for example B. One is using a horizontal arrangement, and one is using a vertical arrangement, which is actually new to me, but it works pretty well. So, using a horizontal arrangement, this is basically just multiple distribution, which I believe is what you were taught in middle school. Multiple distribution meaning multiply this first term in the binomial times every piece of the polynomial that's being multiplied by. Then you'll multiply the negative 3 times every term in the polynomial. So they've done that for you. X times negative x squared, x times 2x, x times 1, and then negative 3 times negative x squared, negative 3 times 2x, and negative 3 times 1. After that, you're simply multiplying and simplifying. X times negative x squared is negative x cubed. X times 2x is 2x squared. X times 1 is x. Negative 3 times negative x squared. Negative times negative is positive. 3 times x squared is 3x squared. And then negative 3 times 2x is negative 6x. And of course, 3 times 1 is 3. We brought down the negative. So then we're combining our like terms. By the way, anytime you're watching this video, if you're thinking, Ms. Brunette's give me a chance to work it on my own before you just give me the answer. Well, pause the video and try it on your own, and then you'll see how you did. Okay, so combining our like terms here, we have an x squared term here and an x squared term here. They're both positive. 2x squared plus 3x squared is 5x squared. And you have x terms. You have a positive x and then a negative 6x. X minus 6x is negative 5x. And then you bring down your negative 3. Okay? So here's your final answer with the horizontal arrangement method. We have negative x cubed plus 5x squared minus 5x minus 3. The vertical arrangement says to write the polynomials vertically, and notice that they have aligned the like terms. They have aligned the x values and they've aligned the constants. But all they did was take the factors and write them one on top of the other with the common terms aligned. Then they multiplied the polynomial on top by -3, just like you would if you were doing a regular multiplication problem. So -3 times 1 is -3. -3 times 2x is -6x. -3 times -x squared is 3x squared. Then they went through and multiplied the x piece by each one of the terms in the polynomial. There's a placeholder because you are lining up your like terms. X times 1 is x. X times 2x is 2x squared. And x times -x squared is -x cubed. The only thing left to do here then is to add up your like terms. -3 is the only constant, so bring that down. -6x plus x is -5x. And 3x squared plus 2x squared is 5x squared. They've already brought down the -x cubed for you. So again, there is your final answer using the vertical arrangement method. And you can see that you get the same thing both ways, which you should because it's the same problem. Feel free to pause if you need to get that down. I'm going to try not to pause because I'm working towards making less 25-minute videos, which I understand is excessive to both of us. Okay. Example 2, back of this page. The top box is about special product rules. There are several special products that occur frequently that it's helpful to recognize their patterns and develop rules for these products. I highlighted these on my sheet, and I think that you should also because you're going to need to know these. You're going to need to not have to flip back to your notes every time. And there are patterns with each one of them, so if you recognize the patterns and look for the patterns, then this shouldn't be too hard. We're also going to notice that when you cube a binomial, we're working towards following Pascal's triangle, which is going to be in the second part of the lesson. Okay, so we're going to use the special product rules and show an example 2. Try to keep that visible. Okay, this says justifying and applying a special product rule. Justify the sum and difference rule. That's the first rule on here, the sum and difference rule. Notice with the sum and difference rule that the first terms and the last terms are the same, just one's addition and one is subtraction. And notice that when you multiply these, you're simply squaring the first term, squaring the last term, and that's a positive times a negative. But when you would FOIL this or do multiple distribution, AB and negative AB would cancel each other out. So we're going to justify the rule first, and then we will show an example of it. Justifying the rule. A times A times negative B times A, and B times negative B. So then simplifying here, A times A is A squared, A times negative B is negative AB, B times A again is AB, and I'm writing it with the A first because you should write your variables alphabetically. And then B times negative B is negative B squared. Now notice that negative AB plus AB are going to zero out, and you end up with just A squared minus B squared, which is what the special product rule tells you. Pause if you need to. So we're going to push this up to example B and show an example of it. Here we have the product 4x squared plus 15 times 4x squared minus 15. The first battle here is recognizing that this is a special product rule. Notice that 4x squared and 4x squared start off both of these binomials. And notice that they both end with 15, but one's adding and one's subtracting. That should clue you into the fact that you're going to use the sum and difference rule. Okay? So using the sum and difference rule, I'm simply going to square 4x squared, and I'm going to square 15, and my answer will be a difference. So 4x squared. 4 squared is 16. X squared to the second power is x4. And then I have minus 15 squared, which is 225. Okay? There's a reflection piece here. We're not going to do the second one, but we are going to do the first one. Error analysis. A student was asked to find the square of 7x plus 3. The student quickly wrote 7x plus 3 quantity squared equals 49x squared plus 9. This is to identify the student's error and provide the correct answer. I've seen most of you do this at some point. So let's think through, what would you do to square 7x plus 3? Squaring something means multiplying it by itself. So using multiple distribution or FOIL, your first terms multiplied together. 7x times 7x is 49x squared. Your outer terms multiplied together. 7x times 3 gives you 21x. Your inner terms multiplied together. 3 times 7x is 21x. And your last terms, 3 times 3 is 9. So when you simplify this, you get 49x squared, combining your like terms, plus 42x, and then plus 9. So what did he miss when he just went straight to 49x squared plus 9? Well, he missed his outer and his inner terms. He missed this piece, which came from this piece, or those pieces. Here's where I would say questions. By the way, if you have questions during this, feel free to comment on the YouTube video. I can see those comments, so y'all can absolutely do that. On example 3, which is the last page we're going to do for part 1, example 3 is applying special products. This is going to introduce Euclid's formula. Just recall that a Pythagorean triple is a set of positive integers, a, b, and c, such that a squared plus b squared equals c squared. Euclid's formula states that if x and y are positive integers with x greater than y, then x squared minus y squared, 2xy, and x squared plus y squared form a Pythagorean triple. So I would like for you to highlight Euclid's formula on your paper and recognize that this is in the form a squared plus b squared equals c squared. Euclid's formula is another one of those formulas that would be handy for you to memorize. So we are going to use this formula to generate a Pythagorean triple with 5 and y. We are not going to verify Euclid's formula, which is why I scratched out example A. Okay? So, using Euclid's formula, it says use the formula to generate a Pythagorean triple with x being 5 and y being 3. So, Euclid's formula was, or is, x squared minus y squared, quantity squared, that's your a, plus b squared, or 2xy squared, equals c squared, or x squared plus y squared, quantity squared. So all we're going to do is we're going to substitute 5 in everywhere we see an x. And we're going to substitute a 3 everywhere we see a y. And then we're going to simplify. 5 squared minus 3 squared, 25 minus 9, here we have 2 times 5 times 3. 2 times 5 is 10, times 3 is 30. Here we have 5 squared plus 3 squared. So, we have A, B, and C as 16, 30, and 34. I'll ask you guys to tell me later, or you can just comment on this YouTube video, which marker color can you see best when I'm up here? So this is to describe how can you check this as a Pythagorean triple. Well, think of the word Pythagorean. A Pythagorean triple works in the Pythagorean theorem. So we can simply perform the Pythagorean theorem on our A, B, and C values. So A squared plus B squared equals C squared. Well, let's see. Does 16 squared plus 30 squared equal 34 squared? Take a moment to punch that out or do the math. Pause it and do that. I'm writing green so you can compare all three colors here. 16 squared is 256. 30 squared is 900. And 34 squared is 1,156. And 256 and 900 do in fact equal 1,156. So yes, this proves that Euclid's formula does work. This is the end of part 1. We are at a little over 16 minutes. I'm going to stop this and we'll record part 2.